Hello, everyone. Welcome to the next meetup organized jointly by quantum computing groups from Washington, D.C., Toronto, and Warsaw. My name is Pavel, and I will be the moderator today. And our speaker today is Sahar Ben Rashid from Universitat Politècnica de Catalunya. So I know that Sahar is now in Barcelona. So it's great that she's joining us from Spain. And the title that we have on the slides is Modular Quantum Computing and On-Chip Quantum Communication Networks. The exact title on the slides from Sahar will be a bit different, but we've agreed that the scope is the same, so the topic is the same. Before we start, just a few announcements. So as you can see, this meeting is recorded, so the video will be later available on our YouTube channel, like usually. And we've agreed with Sahar that this talk can be interactive. So if you have any questions, you can raise your hand and we'll try to interrupt when it is convenient. You can also post your questions on the chat if they are not urgent, and then we can ask the questions during the Q&A session at the end. Okay, and before we start, we would also like to announce the next meetups. So next Saturday, Dr. Jarek Duda from Jagiellonian University will give a talk about electron and neutrino, why they are time crystals, oscillate already in the lowest energy state. So Sebastian will be the facilitator then. And in 2 weeks from now, Terry will give another talk about time in a sparse information universe. And then in July, Terry again will give a talk about the sparse information look at the standard model of particle physics. Later in July, Siyuan Yu will tell us, will give a talk titled Towards Resource Efficient Quantum Computation, Dynamic Circuit Compilation and Optimized Observable Estimation. And then in August, Dr. Kunal Das will give a talk about particle swarm optimization inspired global neighborhood based qubit mapping, a new approach. And then in September, Lydell Aaron will give a talk about factoring with waves, a frequency phase perspective on quantum computation. And September 21st, Dr. Anirbab Mukerjee. And the title is Tensor Factorized Hamiltonian Unfolding to Optimize the Scaling Complexity of the Electronic Correlations Problem on Classical and Quantum Computers. We'd also like to thank our partners and sponsors for supporting this meetup. And with this, I would like to give Zoom to Sahar. So Sahar, first of all, thanks for accepting our invitation. It's our pleasure to have you with us. And if you are ready, the Zoom is yours.
Okay, for the introduction, and thank you so much, Helen, for the invitation. It's a pleasure to meet you, everyone, and thank you so much for taking the time to join the presentation. So my name is Sahar. I'm currently in my third year of PhD in Barcelona Tech, or UPC in Barcelona, and my specific topic is on scaling quantum computers with modular architectures. So we are looking into how we can let's say, overcome the current bottlenecks of scaling monolithic quantum processors. And one of the promising approaches, which is proposed by several groups, but also companies around the world, is the modular approach. So this is an outline of the presentation. I will start with what motivates the proposal of modular quantum computer architectures. Of course, what are the bottlenecks that we are trying to overcome through this method, or let's say this approach, but also which new challenges we are let's say, trying to optimize and trying to suppress, let's say, the overhead of communications that also arises with such an approach. But of course, I will be mainly talking about how that would change how we build the full stack of quantum computation once we try to adopt this approach. And then I would like to, I would say, specifically talk about the work that we are doing in our group. I will talk about our characterization of the communication overhead in such architectures, moving from monolithic processors to modular processors. And then I will be stating the different communication primitives which are proposed as part of building the networks that would connect the multiple processors within a quantum processor or quantum computing system. And then I will briefly talk about the compilation techniques which have been proposed by my colleagues in the group, in which we are trying to modify let's say the currently available quantum circuit compilers in order to be adapted to modern approaches. And of course, that is for the purpose of taking into account the communication operations which are involved into the compilation phase or the compilation level. But also we are trying to minimize the effect of this overhead on the overall computation process for running circuits on real processors. Okay.
So
yes. So in this part of the presentation, I will be mainly talking about the motivation behind the multi-core approach for scaling quantum computers. Okay, could you please go to the next slide? Okay. So a brief, I would say, let's say, statement or let's say talk about the contemporary quantum processing units, which we have seen multiple prototypes coming up in the recent years. These are, I would say, prototypes mainly coming from companies, but also we know that multiple research groups are also working on developing their own. But this is mainly to say that we are mainly at the prototyping phase of quantum computers. We are seeing processors coming up. We are trying, of course, to optimize their functioning. But at this point, we are mainly limited at a few hundreds and at best case, a few thousands of qubits, which are put in the same quantum processor. And I'm sure you are aware of the multiple challenges that is now currently being discussed regarding how we can scale the number of quantum computers to actually have the size of quantum processors that will enable us to run quantum algorithms and actually achieve the potential of quantum computation once the hardware is reliable and stable enough. Now, the currently available hardware is mainly limited to few hundreds of qubits, and they are usually noisy. We still do not have the implementation of quantum error correction. So I would say we are still in the prototyping phase. And one of the approaches in order to scale to the size where we have multiple thousands to hundreds of thousands of qubits within the same system is what we call the modular architecture, the modular quantum computer architecture, in which, in this case, we are trying to have smaller sized quantum processors, which are also hosting, let's say, hundreds of qubits. That's the estimation. And these QPUs would be interconnected via a quantum processor, a quantum communication network. The quantum communication network will enable the transfer of quantum states from one QPU to the next in order to ensure the application of, I would say, 2-qubit gates mostly across the distant qubits or the distant processors. And the main challenge that we are trying to overcome using the modular approach is the bottleneck of packing multiple qubits in the same processor, which would accelerate the process of decoherence of qubits, but also it will amplify the effect of crosstalk. That's when we have the clash of frequencies once we try to control qubits, but also the complexity of the control system. At this point, there are, of course, different proposals to optimize the control and readout system of quantum computers. But at this point, we are still relying on cables and direct connectivity of the control system to the qubits. And this is, of course, becoming more of a bottleneck as we are increasing the number of qubits per processor. And one of the one of the solutions to this problem would be to rather use a modular approach in which we have smaller size QPUs, which are more stable and much easier to control. And it's the communication network that will be the key to ensure that quantum algorithms can be implemented on such an architecture. Okay, next slide. So, If we follow, for example, the roadmap for IBM Quantum, we may see that the approach of modular quantum computers is also part of their roadmap in the sense that this is also considered as a viable approach in order to scale the number of qubits. And it is expected that by 2028, we can have a prototype of modular quantum computers, a modular quantum computer in which we have a network that is interconnecting multiple processors, small size processors, and it will enable the application of quantum gates across the distant qubits. But of course, we need to be, I would say, also aware of what compilation process will be implemented by IBM Quantum at this stage, because for them it will be mostly of cutting and knitting, which is a very particular approach to the application or the running or the execution of quantum algorithms over these processors, in which we have, I would say, the splitting of parts of the algorithm, in which we will have each part to be executed on a different processor, and then there is a post-processing phase in which we have the assemblage of the results to have a final outcome of the processor, of the processing unit. But technically speaking, this is a very different compilation process that we are not working on in my group. But definitely, of course, it's worth knowing more about, since IBM Quantum, I think, has already started publishing, I would say, their approach and how they will be modifying their compilers in order to adapt to the modular approach that they will be building. But fundamentally speaking, this slide is mainly to say that even IBM Quantum is considering this approach as a viable approach to scaling quantum computers. And eventually, this is going to be how they will be building the advanced systems, which will be hosting hundreds of thousands of qubits. And of course, on top of that, we will have the optimization and the different quantum error correction protocols being implemented on this approach. And everything comes down to how we built this layer, the physical layer of processors, because it needs to be taken into account for the compilation level, but also for the networking level and the management of the circuit compilation and execution over processors. So next slide. Okay, so this is, I would say, one of the early, I would say, papers that was released by my group, in which there is a motivation for the introduction of modular quantum processors, and this is mainly to say that once we start building modular quantum processors, we need to take into account the added communication overhead to be managed and optimized by higher levels of the stack. So we have at the physical layer, in which we have the qubit technology, and then we have the building of processors and the networking primitive or the communication primitive that will be adopted. In this case, we are relying mainly on entanglement protocols. But of course, it's not the only option. I will be talking about which different communication primitives are now being, I would say, researched and developed. But in this slide, I will be mainly presenting the communication network, which is dependent on entanglement, generation, and distribution, and eventually relying on the teleportation protocol in order to transmit the quantum state from one processor to the next. Now, this is a very, I would say, costly operation. The teleportation itself, it's an entire protocol that will indeed add more gates, but also a communication overhead, and technically speaking, also more noise. And that needs to be taken into account also at higher levels of the stack. For example, the networking layer, and also the compilation layer. So this is when we talk about the full stack quantum computation that needs to take into account the application that we're trying to execute, but also the underlying architecture in which we have the computation stack, but also the communication stack. So next slide, please. Okay. So now we have now we need to take into account the communication overhead that will be added besides the computational process or the computational workload for the execution of our application. Now, how can we assess, first of all, quantify this overhead, but also assess it and try to find ways in order to optimize it and also suppress its effect? So here I would say, while the modular approach may seem very promising, We need to also say that it also comes with its own challenges. Quantum communication can be a costly operation to add, and also if we are talking about the compilation of large-scale circuits, since we are talking about scaling quantum computers, then we will see that there is a very important communication workload to be added into the compilation phase, and therefore we need to take it into account and we need to find ways to suppress its negative effect. So in this work, we are proposing performance metrics that will rely on quantifying the communication overhead, that is mainly the communication operations that will be added during the compilation phase of circuits. And also, we are trying to characterize the traffic that is mainly referring to how the qubits are being moved from one qubit to the next as we are executing the circuits. So in this work, we are proposing mainly 8 performance metrics that will be mainly taking into account the communication operations, but also the computation operations. And we are trying to see what is the ratio of for example, the computation to communication ratio, in which we are trying to see whether the communication workload is I would say very high, such that it penalizes the computation workload, or whether in certain applications it is still manageable and maybe its effect would not be as negative as maybe we are assuming. And we mainly took into account these performance metrics, but we also considered the execution of also the compilation of multiple circuits to see whether the different structure of circuits would also have an impact on the distribution of the communication overload. Okay, so the performance metrics. First of all, we consider the computation to communication ratio, that is mainly taken into account the number of communication operations, but also the computation operations. And then we took into account the locality, that is mainly the number of teleportations, the number of operations of teleportation which are added to the compilation phase, and also the qubit stay time, which is mainly taken into account the ratio of the duration that the qubit would be installed, I would say, in one processor over the total execution time of the application. And then also we took into account the performance metrics that would quantify the resource usage uniformity. So that would be the mean qubit hotspotness. This will tell us whether some QPUs are being used more than others during the execution phase, and that would be the variance to the mean of the number of operations applied per qubit. We have also the mean core hotspotness that takes into account the teleportation, the number of teleportation operations per core. That's also the ratio, the variance to the mean of the number of teleportations. We also look into what is the longest gate sequence that is being applied in this application. That mainly takes into account the different applications, the different operations applied to qubits, and then we take the longest sequence. And then we have the qubit lifespan, in which we discrete the execution time over what we call time slices, which are of course of equal durations. And then we took into account, and then we look into what is the longest, I would say, consecutive, the longest series of time slices that is consecutive, in which we have the application of an operation of a specified qubit. And then we have the temporal burstiness, which is the variance to the mean of the teleportations per time slice. What we are trying to look at the through the temporal burstiness is that whether the compiler is, I would say, whether it is specifying certain time slices as communication time slices, and then it starts the computation workload. And in this case, it means that the communication overhead is delaying the computation overhead, or is delaying the computation process, sorry, or whether the compiler is actually distributing the teleportation operations more or less, I would say, in a balanced way, such that the communication and the computation operations are being applied in parallel. And of course, that would be the ideal case because we don't want the communication operations to be delaying the computation process. And that means that we are mainly, I would say, delaying the execution of the actual application at the expense of prioritizing the communication. So these are the different performance metrics that we, let's say, come up with in order to define a framework for quantifying the communication overhead and eventually propose ways to eliminate or, let's say, suppress its negative impact on the computation workload. So it's also very important to say that in this work we have compiled 8 quantum circuits over a very specific architecture. The specific architecture assumes an all-to-all connectivity within one processor, but also the all-to-all connectivity between processors. And we know that this is an ideal case. Okay, so technically speaking, the currently available processors are constrained in terms of connectivity between qubits, but also most of the communication primitives being proposed will also impose a constrained connectivity between processors. However, there is a tendency to develop an all-to-all connected processor and an all-to-all connected modular processor, and this is achievable in certain cases. For example, trapped ion processors tend to be all-to-all connected. But also, if we are relying on networks which are using entanglement generation and distribution, it is possible to have the setup connected to all the QPUs in the same system. So what we are assuming in this work is a very specific case, but that doesn't mean that the performance metrics cannot be extended to other more architecture constrained setups. Okay, so that's why all the results that I will be presenting, starting from the next slide, are very specific to the implementation of circuits that we have chosen, but also to the architecture that we have assumed. And this may be, I would say, a very specific case that we are talking about, but the main contribution of this work is mainly the proposal of the performance metrics, which we are, I would say, introducing as a way as building a scalable framework for the quantification of the communication overhead and optimizing it. Okay, can we please go to the next slide? Okay. Okay, so before going to the modular approach, I wanted to briefly go over the monolithic processors. In monolithic processors, we also talk about the communication overhead. Okay, and the communication overhead is actually the additional swap operations that must be added also at the compilation level in order to make sure that every time we apply a 2-qubit gate, the 2 qubits must be placed in physical proximity. Okay, which is the currently, I would say, known way of applying 2-qubit gates. So every time we need to apply any type of 2-qubit gates, we need to make sure that the qubits are moved so that they are placed into physical proximity. This is, of course, taken into account the constraints of connectivity between qubits in a certain processor. In this case, we are mainly looking at the application of the Grover's search algorithm on a 64 qubit processor. So if we look at the figure on the left, this is considering an all-to-all connected processor. Okay, this means that any qubit can interact with any other qubit. And this means that we don't need to take into account the architectural connectivity constraints. And if we look at this figure, the computation operations are in red, and everything in black are actually idling qubits, or let's say qubits which are not taken into account for the computation process. So what we look at is actually the distribution of gates once we execute the Grover circuit over a 64 qubit processor that is all-to-all connected. So as you can see, it is reflectant of the diffusion, I would say, and repetition cycle that is implemented within the Grover search algorithm. And practically speaking, this is very much reflective of the virtual circuits of Grover's search circuit. Now, If we move to the second figure, here we are mainly taking into account the constraints of the architecture in which we have a star topology. The star topology is when we have the first qubit, for our assumption, the first qubit, it is connected to all the other qubits. Okay, the star topology was mainly considered for the very early prototypes of quantum computers, but I think now it's not considered as anymore, because it's first of all, it generates a very hot spotness on the qubit in the center, and therefore it is not scalable, but also it does not allow the parallel distribution of gates. So technically speaking, this is not, I would say, a viable topology, but this is just to give an example. But if we can see in the star topology in which we have the qubit 0 that is connected to all the other 63 qubits, we may see that there are additional gates which are added at the compilation level in which we are representing in white. And those white operations are actually referring to the swap operations which are added in order to make sure that the gates are, the two qubit gates are always implemented over two qubits which are interconnected. And therefore, every time we need to apply a two qubit gate, we need to, I would say, swap the qubit to the position of the qubit 0 in order to have a direct link between the two interacting qubits. And as you can see, it is mainly adding a lot of communication overhead that is applied mainly to the qubit 0, and that's why it is generating a high hotspotness. Now, if we consider more realistic architectures, first of all, we are considering the heavy hexagon, which is the architecture from IBM processors that is now also being considered even for their newer, even if we are considering newer processors. And as you can see, there is also an addition of multiple swap operations, which are completely changing the original, let's say, structure of the virtual circuits. And this is mainly a visual representation of what it means to add a communication operation to the compilation level. And as you can see, this is, I would say, importing, or let's say adding multiple operations to the execution process, which may hinder the optimal execution of the application. And if we look at the last example of an architecture, also the square lattice. The square lattice is just a simple 2D grid. And while it does not have the ideal connectivity of an all-to-all, it is still, I would say, a viable architecture to consider, since the amount of operations which are added in this case are not as worse, I would say, as the heavy hexagon or star. But of course, this is a comparison between 3 or 4 architectures. If we need to take into account more architectures, then visually speaking, we can compare between which one would be more viable and which one would be best for reducing the communication overhead. Okay, so can we go to the next slide, please? So the visual representation is good, but of course we need more tangible metrics in order to quantify this communication overhead. Just a reminder, the communication overhead in this sense is just mainly the quantification of the swap operation which are added. For the star topology, if we look at the communication to the computation ratio, we may find that it's very low. Okay, so it's very low. And why is that? It's because we are always one swap away from any operation. However, if we look at the star topology hotspotness, mean qubit hotspotness, we may see that it is quickly rising and or increasing, and especially for complex circuits such as the QFT, the quantum Fourier transform, or the QAUA02. This is the QAUA circuit that we are considering in this case is actually taking into account the input graph of a random graph of edge probability of 0.2. Okay, and then we have the Grover circuits and we have the Cuccaro circuit. The Cuccaro circuit is how we do the addition using quantum computers. And of course, we may see that the mean qubit hotspotness is clearly different from one circuit structure to the next, but overall, the star topology is always characterized by a high hotspotness, especially as we are scaling the number of qubits per circuit. And for complex circuits, which are mainly the random and the QFT, they are very much costly. For the system burstiness, this is mainly dependent on how you choose your compiler. For our compiler in this study, we consider the OpenQL, even though it's not as used at this point, but it's definitely one of the compilers that can be used in this case, and also it has an extension to modular quantum computers, so that's why we used it. For the system burstiness, this is mainly saying that the compiler is mainly distributing the operation of swaps more or less in a balanced way between the different architectures of circuits that we have considered. Is there still a problem with the presentation?
Somebody requests to make it to 100.
It is
I think
100 now.
100 is not the best.
He asked for 125.
25?
125%. It's a 125%.
The problem was the slide wasn't all the way up, and so the bottom of the slide was cut off.
Oh, okay.
Incidentally, is there a way to get rid of the Team Orion X? We didn't originally have that label over it covers some of the text.
Yeah. Yeah, I think that's moving, and it's okay. But I think I'm always keeping the main content of the slide somewhere in the middle. So I think at the end I'm mainly mentioning the citation and the logos of the group and the university. Okay, so how do we position the slide so that it's mainly covering the main content? Is 125 still good, or do you mainly prefer it to be at 150?
125 looks good on my screen.
Okay, perfect. 125. I think we can keep it. Okay, now if we go to the heavy hexagon topology, which is IBM quantum processor topology, we may see that the CCR, or the computation to communication ratio, is higher than the star topology. And this is mainly because you would need to add multiple swap operations in order to make sure that your two qubits are positioned next to each other at any point. So technically speaking, the heavy hexagon is a very, I would say, it's a very constrained architecture. I still do not have a good idea of why it is chosen by IBM, but still, I mean, at this point, I think they are using it for scaling as well. But if we look at the metrics, it may not be the best choice in which we consider the communication overhead as a hurdle to be added to the compilation process. But this is mainly as an introduction to how we can quantify this communication overhead by comparing the additional communication operations to the original application gates. And of course, it is scaling as we are increasing the scale or the size of the circuits. Now, for the qubit hotspotness as well, yeah, since we are adding many communication operations to the compilation phase, so that means that some qubits are being used multiple times, not even for the computation, but also for the communication, and that may stress the qubits. And of course, eventually, if we are talking about the execution on real hardware, that will be mainly a challenge considering the decoherence constraints of qubits. And for the system burstiness, in this case, we may see that it is mainly at larger scales of the circuits that we may see that there is a change in the pattern of the distribution of the communication process, of the communication operations during the compilation process. But overall, it is still kept low because of the type of compilation algorithm that we have used. And if we go to the next slide, this is for the square lattice topology. Now, if we look for the square lattice topology, we find that it is laying somewhere in between the star and the heavy hexagon, in the sense that yes, the communication to computation ratio is increasing as we are scaling the size of the qubits, but it is still manageable in the sense that even for a QFT of 64 qubits, the CCR is less than a half, it is less than 0.5, and therefore we may find that it is more of a balanced distribution of gates in comparison to the heavy hexagon. For the hotspotness, also due to the constraints, we may see that the QFT will be mainly generating a hot spotness for the qubits. And of course, that needs to take into account the type of application that we are aiming for, but also how we can limit the impact of the communication process. And also for the burstiness, it is mainly, there is a change of pattern if we are increasing the size, but overall it is still kept balanced by the type of algorithm that we are using. Now, of course, even in this study, we are considering mainly 4 circuits and 3 architectures, just to give an example of how these performance metrics can be used and how we can quantify the communication overhead. And if we want to do sort of a comparison between which type of architecture is best for certain applications, then of course this can be one of the frameworks that can be used. Now, if we go to the next slide. Okay. Now, it's more or less the same exercise, but in this case, we are considering a modular architecture in which we have the compilation of, in this side, we have 4 algorithms. We have the GHZ, which is the circuit that generates an entanglement at the circuit level. We have the quantum Fourier transform. We have the QAUA circuit with a random graph input, and we have the VQE that considers an ansatz that applies a C naught in a sequential way. Okay, so not in parallel, but rather in sequential way. Now, these are very specific circuits, and this is also the same exercise in the sense that we want to visually see how the application of the teleportation operation between processors changes the structure of the original circuit. Now, again, the red is the computation gate, and the white is the communication gate. The communication gate would be mainly referring to the application of the teleportation protocol. And if we look at the top circuits, these are the virtual circuits. Okay, so this is when we are considering a 64 circuit virtual circuit. So that means that we don't consider the constraints of the architecture. And then if we look at the second row, this is how the circuit changes once we compile the application to a very specific architecture that considers 16 qubit per core, and we have 4 cores. So the total would be 64 qubit, but in a modular setup. And as we can see, for the GHC implementation, we are mainly considering that the first qubit is connected to all the other ones, and that's why we see that there is the movement of all the qubits to the first core. And if we look at the QFT, also the additional number of teleportation processor changes the structure of the circuit, but also it makes the operation application more sparse. Same thing for the QAUA and same thing for the VQE. So how, of course, besides the visual representation, how can we quantify this communication overhead? So if we go to the next slide. So I have already introduced the 8 performance metrics that we are considering for a modular architecture. Okay, and here we compiled 8 circuits, and for each circuit we consider different sizes. So 4 cores of 16 qubit each, 16 core of 16 qubit each, and 60 core of 16 qubit each. So we compiled circuit up to 960 qubits in total. And we wanted to look at, okay, what is the result communication overhead if we try to implement these circuits over this modular setup. There is still an issue with the slides?
I think it's not a big issue because we also moved the slide, so I can see this team Orion X on the screen as well, but I think that, we should. It's. I think it's not a big problem. Don't worry.
Okay. Okay. So we did this analysis for two type of setups. The results that I will be presenting for this slide and the next one will be for what we call the strong scaling regime. For the strong scaling regime, we fix the number of qubits per core, in this case to 16, and then we add cores. Okay, so we have 16 per core, and then we start adding the number of cores until we reach 60 cores, 16 and 4. And there is also another regime that we refer to as weak scaling regime, in which we fix the total number of qubits, and then we start splitting them over the number of cores that we want. Okay, so for example, we fix them at 512, and then we put them in one core, and then 2 cores, and then 4, and then until we get to 16, I think. Wait, yeah. Okay, I will verify in the analysis. Sorry. Okay, let's focus at the strong scaling regime. So the strong scaling regime, I would say, is a very natural way of thinking of modular architectures, right? We have smaller scaled processors, and at 16 qubits, they are stable enough, I would say. I think we have the technology at this point to build quite good prototypes of 16 qubit processors. Now, how about we connect them in order to reach to the number of qubits that could be approaching to thousands of qubits per system? And that's when we start to take into account the communication overhead. And if we look at the CCR of these circuits, we may find that it is quite high, in the sense that the additional communication operations are not negligible, and therefore their impact need to be assessed and need to be optimized. If you see that the QFT and the QAUA circuits are missing, it's because the compiler just crashed at this size. So technically speaking, we compiled circuits up to the size that they were compiled. If they are not appearing in the results, that means that we could not really get a result. It just crashed. Okay, and this is mainly to talk about. I will just open this parenthesis to talk about the type of circuits that we have chosen. So we chose to compile 8 circuits: the Cuccaro for the addition, the Grovers, the GHC for the entanglement generation, quantum Fourier transform, which is a very complex circuit, QAUA 02, which is a very specific implementation of QAUA that considers a random graph as an input. And then we have the QAUA WS. WS, I think it's more of a structured graph. So technically speaking, we know from the beginning what type of distribution of gates we are dealing with, and it's more of a structured I would say, distribution of gates. And then we have the QAUA that implements 2 types of ansatz. The first one, which is the hardware efficient ansatz 1, that considers more of a sequential application of CNOTs, and the second one considers a parallel application of CNOTs. And you will see that the choice of ansatz and the choice of the input graph is very important, because if you choose the ansatz in a certain way, it will determine how your gate distribution will be like, and therefore it will impact the communication overhead. And therefore, this type of application does not only help in order to quantify the communication overhead, but also if you need to do a decision in order to have a more efficient application of your algorithm without, I would say, a negative impact of the communication overhead, then this type of assessment can help you to make that decision. Okay. Now, if we continue to look at the locality metrics, which are mainly the number of teleportations and the average stay time. Now, of course, in general, as we are scaling the size of the circuits, we may see that the number of qubits are the number of teleportations and the average stay time is increasing. That's I think quite trivial. But if we see the QFT and the QAUA, which are very computationally heavy instances, we need to look at mainly the number of teleportations which are added. So for example, at 16 cores, which is 512 qubits per architecture, the number of teleportations which are added to the compilation is hundreds of thousands. So this is just to say that, of course, they are computationally heavy or computationally costly algorithms, but also part of that cost is coming from the communication process itself. Okay, and of course, having a knowledge, I would say, or an assessment over how many teleportations you will be adding will also give you more information on how to optimize the generation and distribution of algorithms of the entanglement and the application of the teleportation operation, but also how you can distribute these teleportation operations such that it doesn't negatively impact your computational load. And of course, if we have a high number of teleportations, that means that the qubits are moved more frequently, and that's why it is directly reflected in a low average qubit stay for these two instances. But for the other algorithms, I would say, we may see that the Kukaro is more balanced, such as the Grover as well. GHC also, it is getting more complex, mainly because it depends on how you are distributing your state. In this case, we consider that the first qubit is connected to all the others. So that means that all the other qubits must be moved to the first qubit for the application of gates. And that is also a very costly operation. But also, if we look at the choice of the graph, then of course it's very important. It's very apparent that a more structured graph is better handled than a random graph. And for the two type of ansatz for the VQE, it depends on what you want to prioritize. But of course, in this instances, it's more balanced. We will see the difference in more in the other metrics. Okay, can we go to the next slide? I will try maybe to move a bit faster. Oh, it's already almost 1 hour. Okay, so if we continue also to use the exact same metrics, such as the mean core hotspotness, the qubit hotspotness, the system burstiness, this is more on the quantum algorithm, the longest gate sequence, and the qubit lifespan, we may see that the structure of the circuit is a very important element to consider for such exercises. And if you want to make decisions on which implementation of circuit would be more efficient for a certain setup, we believe that this type of framework would be helpful in that. For example, yes, I think I already made the conclusion regarding the two implementations of QAUA. Definitely more structured graph is better for limiting the impact of the communication overhead. But also, if we look, for example, at the system burstiness, it's very, I would say, at least we observed from our implementation is that the distribution of the teleportation operations is different because already how you arrange the application of CNOT gates is different for the two type of VQEs. So the two last circuits. And we see that if we are scaling the circuit and we are mainly considering the second type of VQE ansatz, which is the application of CNOTs in parallel, then of course that means that there will be higher burstiness in the sense that the algorithm will be allocating certain time slices only for communications and other ones only for computations. And of course, if we want to have more of a balanced workload, then definitely a sequential application would be more helpful in this sense. But of course, that depends on what you want to prioritize. Okay, next slide, please. Okay. So we did the exact same analysis, but in the weak scaling, in the sense that we fix the number of qubits and then we add the number of cores. We implemented the circuits for 512 qubits. We didn't go up to 1000 simply because the circuits just did not get executed. But they are still, I would say, a high number of qubits in one circuit. So I think the size is good enough. And yes, so more or less the conclusions are the same in the sense of, okay, how many teleportations will be added? How is the CCR doing, I would say, in terms of distribution of gates? But of course, this is mainly to find ways to see what would be the best approach to scale these circuits. Is it the weak scaling in the sense that you have smaller size QPUs and then you start adding the same number of qubits but in multiple QPUs, or it's the same it's the same it's the same approach, but rather you have packed, I would say, a higher number of qubits per QPU, and then it's just a matter of how you want to distribute your workload. But I would say the conclusions would be more or less the same. Okay, I think we can go maybe to the other section. Yes, this is more of a quantification also of the same overhead. Okay, the on-chip communication primitives, which are now being considered. Okay. So in this work, yeah, we can go maybe to the 19th slide. Yes, this one. Okay. So in this work, we relied on what we call a design space exploration in order to, I would say, evaluate the current state of the art, but also to see what we need to improve in order to make sure that our communication networks are efficient and are scalable. What is a DSC? So a design space exploration framework starts with modeling. So which parameters are mainly to take in, which metrics, first of all, are taken into account in order to form a figure of merit, which parameters are making up your performance metrics, and how do you define your figure of merit in the sense that what do you want to prioritize and what do you want to minimize. Okay, so if you come up with a figure of merit, that will be more of an evaluation metric, I would say, that will enable you to, I would say, not position, I would say, but it will enable you to assess the efficiency of a certain configuration. So if you have a configuration that is mainly characterized by a mix of your parameters or a mix of your metrics, it will eventually be represented by a certain point with your figure of merit, and then within several configurations, how do you elect the best performing one? But also, if you want to improve, which metrics that you need to work on and which metrics that maybe you need to minimize its effect. Okay, so in this sense, yes, and why we need the DSC framework, that is mainly to do the evaluation of the performance trends, but also if you want to do the optimization of the design. You need to set your objectives, and then according to those objectives, you need to the figure of merit can help you to define which direction of improvement is feasible. Okay, so for this work, we wanted mainly to evaluate the current state of the art for the different communication primitives which are proposed to build a network of quantum communication that will be used for interconnecting multiple QPUs. The communication primitives that we came up with can be mainly summarized in three categories. There is the cavity-based interconnects. There is the transaction-based networks. I don't know. We can stay in the 19th. Okay, we have the cavity-based interconnects. We have the transaction-based networks, and we have the entanglement networks. So the cavity-based interconnects that are usually reliant on microwave cavities, optical cavities, or waveguides in order to interconnect two qubits, and they can be placed in different QPUs. Okay, the transaction-based networks are also considering two qubits which are interconnected by a cavity, but they add transducers. And transducers are elements that convert optical photons to that convert microwave photons to optical photons in order to enable their transmission with higher fidelity and for longer distances. Okay, and then we have the entanglement networks. The entanglement networks can be the ones that enable the teleportation protocol, but also there is also just the application of telegates or teleported gates. Okay, so this is a type of protocols in which you don't have to fully implement the protocol of teleportation, but you can rely on the distribution of the entanglement in order to enable the direct application of gates by the entangled states that you share between two specific qubits. But also there is the entanglement heralding. There's also the entanglement distillation protocols, which are included in this category. So it really depends on what is the communication protocol that you want to build eventually. But at the core, it is mainly the quality of the distributed entanglement that you are generating that will be a very key factor in order to decide on the success or the failure of your operations. So these are, of course, very general three categories because it's a very active area of research. Actually, there are many proposals of different variants of these communication primitives. But eventually, if you want to have more of a generalization, we can put them in mainly three categories: cavity-based, transaction-based, and entanglement networks. Now, we also propose a figure of merit that will enable us to compare the efficiency of the different proposals, but also to help us to decide on which direction would be feasible to improve the currently available solutions. So the proposed figure of merit would include the efficiency of the generation of the quantum states already that we want to transmit, the area efficiency, which is mainly the interface area between the communication channel and the qubit. This is actually an important detail, but I think in quantum it's still I would say it's not prohibitive element. So technically speaking, if you want to talk about the scalability of the communication primitives, then it's a very important element to consider. But at least for the currently available prototypes, it is not a prohibitive element of the configuration. And then we have the latency of operations, that is mainly how much time is added as an overhead in order to enable the application of gates that we want to apply, and also the infidelity. The infidelity is directly linked to the fidelity, and it is mainly quantifying how good or how reliable is your operation that that you are trying to generate with the communication primitive that you choose. Okay, maybe we can discuss more in detail in the next slide. Okay. So if we talk about the cavity-mediated interconnects, the cavity-mediated interconnects are usually setups which consider the connectivity between two qubits, and we have the communication channel between them that is mainly relying on microwave channels, superconducting cavities, optical cavities, and waveguides. Okay, these are usually what we find in this category. And there are mainly three elements that determine the success or the failure of the quantum state transmission through the channel. This is the coupling strength between the qubit and the channel, or the qubit and the cavity. We have the cavity decay rate, kappa, and we have the atomic decay rate, which is gamma. So G is mainly determining how strong are your systems interconnected, and that would enable you to have fast and more reliable operations. Kappa will quantify the noise that is generated at the cavity level that will mainly degrade the fidelity of the state that is being transmitted. And gamma is mainly quantifying the noise that is happening at the qubit level, which can be directly correlated to the T2 time of the qubit. Now, if we look more into detail, we can quantify the efficiency. No, we are still in the same slide. Yeah, we can, in the system, we can quantify the efficiency by the success probability of transmitting the state from the qubit to the photon that will be transmitting the quantum state through the channel. Okay, these are usually virtual photons, and they would be holding the quantum state that you want to transmit. And the efficiency of the operation is pretty much dependent on how successful is that transmission of the state from the qubit to the photon that will be holding the state. And this is mainly dependent on the kappa factor, so that is mainly the noise at the cavity level, but also the cooperativity factor, which is the C. See, the cooperativity actually is itself a figure of merit, and you may find it in several papers already. The cooperativity is the ratio between the G factor and kappa gamma. So usually you find it G squared over kappa gamma factor, and that is mainly quantifying your coupling strength versus the noise factors. And if you have a high G, then that means that your system is more or less resilient against the noise that is coming from the channel and the qubit. But if you have a weak G, then that means that the noise is more of a dominant factor of your process, and eventually that is an indicator that the system will be failing. So ideally, what you want to have is a strong G and weak kappa and weak gamma. Of course, that's the ideal case. It is very hard to achieve, as we will see in the comparison. But that is, of course, the goal and the objective of all the works that is mainly relying on quantum state transfer and entanglement generation across cavities. The latency is dependent on the quality factor of the cavity, but also the frequency of the cavity. The infidelity is mainly related to the cooperativity factor. So the cooperativity again is G squared by kappa gamma, sorry. And of course, the infidelity is mainly quantifying how good will be the entire process. Okay, so if we go to the next slide, usually what we find in the even in the proposals for modular quantum architectures, you may find that the 2D grid is a very viable architecture. But of course, since we don't have an experimental validation, that is too early to conclude on. But I would say among the most viable proposals would be the 2D grid with cavity interconnects. And technically speaking, this is becoming more of a topic of research and development for multiple groups, simply because cavities are versatile, but also there is enough knowledge about the dynamics of the qubit cavity system, that is mainly the quantum electrodynamics theoretical framework, that enables researchers to have more of a resilient system and eventually build a very reliable quantum communication channels. Okay, this is more of a comment than a statement, but I just wanted to share with you just to keep it in the back of your minds in case you want to have more of a deep dive into quantum communication channels. Okay, so if we consider cavity-mediated coherent links or quantum communication channels, and again, of course, we are considering these type of metrics in order to build our figure of merit. And we also looked at, okay, maybe this is not clear, maybe we can zoom in more, but we consider several, yeah, just to go to the right part of the slide. Yeah, so we looked at the G, kappa, and gamma factors from different experimental works. Okay, and then we did more of a comparison between state-of-the-art solutions to see where they fall out, I would say, and whether they are good enough to ensure a high-fidelity transmission of quantum states across cores. So this is the list of experimental works that we have considered, and as I said, we picked mainly their numerical values for G, kappa, and gamma, and then we did more of a comparison between the different works in which we are relying on the figure of merit as our element to do the comparison. The higher the figure of merit, the better, because that means that we have a high efficiency, low latency, and low infidelity, which would be the best case scenario. But as you can see in the yellow zone, let's say, which indicates a high figure of merit, we find that most works do not get to that level yet. And that is quite normal, I would say, because the qubit quality is still not as good as it should be to ensure I would say, frequent interactions with the qubit and also multiple connections to the qubit. But also, the technology of cavities is still not advanced enough to ensure the transmission of quantum state at the level that we would like it to be. Of course, it's quite advanced already, but it's not as much as it should be. What we find is that most of these systems fall in what we call a weak coupling regime or intermediate coupling regime. What is a weak coupling regime? This is simply when we find that the noise factors, kappa and gamma, are higher than the coupling. Sorry. The weak coupling regime is simply when we find that the noise factors kappa and gamma are higher than the coupling factor between the qubit and the cavity, that is the parameter G. This means that the noise is much higher than the interaction between the qubit and the cavity, and that means that it is a dominant factor, and eventually it will lead to the failure of the operation. What we want to do is to move from the weak coupling regime to the strong coupling regime. The strong coupling regime is when the G factor is much higher than kappa and gamma, so that the G factor would compensate for the noise effects. Now, if we look at the comparison, of course, we can only compare two at a time. The figure of merit, if we want to consider the G and kappa, usually the systems are very much located, or let's say characterized by a weak coupling regime in which kappa is still too high, but also gamma is still too high, even though we may find one work by Evans et al. That has achieved more or less, I would say, a fair enough, or let's say a good enough ratio between G and gamma, but still their kappa factor is too high to place it in a strong coupling regime, and that means that we are still a bit, I would say, we are still far away from achieving the optimal regimes that ensures a high fidelity transmission of quantum states through cavities. Okay, so this is mainly what we try to do in this part of this work. I think we can go to the next slide. Yeah, okay. So the last figure that is mainly to enhance or to emphasize the impact of G. So G factor is, I would say, one of the key elements that we need to focus on in order to improve the quality of the transmission of states through cavities. Simply because if we improve G, then we can compensate for the effect of noise, and eventually that will enable us to have a faster transmission of states, but also high fidelity. And that means that we need to work into the strong coupling regime rather than the currently available systems which are working in the weak coupling regime. So that's mainly the conclusion of the work. So, but also besides the cavity systems, we may find transduction-based networks. What's the difference in the system is that we add transducers as part of our network. Transducers, as I said, would convert the microwave photons into into optical photons, and that will enable them to be traveling at faster. Not faster, because it's eventually it's the speed of light. It's the same thing, but I think it will be traveling with a higher fidelity. Okay, but technically speaking, this is a system that is too bulky to insert into a modular architecture. So even though it has been considered in certain experimental setups, we don't think it is a viable approach. First of all, because the addition of transducers is already a hurdle, but also the efficiency of transducers is very low at this point. Even though they have been improved over the years, their efficiency is still very, very low in order to ensure that it does its function as reliably as possible. And of course, we are talking about quantum states, so they are already fragile. And if we want to add more elements that would add more noise into the equation, then I don't think this is a viable approach. At least this is also a comment more than a drawn conclusion. But of course, since it is being developed, then we also consider it for the work. This is a work in progress, so I still haven't done more of a comparison between the different proposals. But this is more of an introduction of what are the type of primitives which are being explored at this point. So the transducers are very important elements to add into this system, and practically the efficiency of the process is dependent on the efficiency of your transducer. So even if we talk at the efficiency level, this is mainly an equation that quantifies the efficiency of the transaction operation itself, which also takes into account the cooperativity factor. But the cooperativity factor in this equation is different from the one in the cavity. Why? Because it takes into account the coupling between, let's say, the microwave photon and the optical photon, but also the noise coming at the microwave mode and the noise coming from the optical mode. So we are mainly reducing the efficiency of the process to the efficiency of the transaction operation itself. That's mainly to highlight how important this is. Okay, so yes, for the latency also we are mainly relying on the G factor. The G factor is also the coupling strength between the two modes, the microwave mode and the photon mode and the optical mode. But also we have the quality factor of the cavity and the frequency of the cavity. The infidelity, as I said, is also relying on the cooperativity factor in the sense which also takes into account the coupling strength and the noise coming from the two modes. Okay, maybe we can go to the next slide. Now, for the entanglement. Okay, this is of course a very simplistic scheme of what an entanglement network would involve, but also the entanglement network would necessarily include an entire setup for the generation and distribution of entanglement. And of course, this is a technology that is still not mature, I would say. It is still in development, but also it is still not as good as we would like it to be. And while entanglement networks are very promising, as I said, for the implementation of the teleportation protocol, but also for the implementation of teleported gates, inserting this setup is still too bulky for a modular architecture, and also it is still a source of great noise. So we know that the entanglement generation rate is still very low. I think for the best experimental works, I think they have one successful maybe generation of entanglement per 10 minutes. I think that was one of the best ones that I read in the experimental proposal. So that is still very low. If we talk about compilation of circuits that would need more than, or let's say hundreds of thousands of teleportation operations to execute, and we are talking about entanglement generation rate for 1 per 10 minutes, that is, I think we are still very far from a confident reliability on entanglement generation networks. But of course, since it is still being explored, then it is worth talking about. Also, so we have mainly the generation rate, we have the generation time of entanglement, because also especially if we add distillation in the process, it is a time-consuming operation, or let's say cycle, which of course improves the fidelity of the entanglement that is being generated, but at the same time it adds a lot of time. And of course, time is mainly linked to noise in quantum computing. And therefore, if we want to optimize entanglement networks, then we need to work on multiple levels. That would be the generation rate, the generation time, but also, yeah, the decoherence time of qubits. What's I think it was the... Sorry. Okay, maybe I need to verify what is the D element or parameter, because sorry, I need to verify this one. But it's mainly related to how we quantify the latency. That is mainly the additional time that is required in order to generate and distribute entanglement. Okay, if we go to the next slide. Also, so within the same, I would say, approach. So we looked at the different experimental proposals. We looked at the numerical, we looked at the numerical let's say, parameters taken from each reference, and then we tried also, based on the figure of merit that we have, we tried to do more of not timeline, but it's more of we wanted to see how the evolvement has been, the evolution, sorry, of the systems has been going through the years. And of course, this may be more of a visual comparison between the different experimental proposals from state-of-the-art communication primitives, but also it can give us an idea of what approach is better, or let's say is best for the development of scalable quantum communication networks. And if we just look at this comparison, we have the cavity-mediated interconnects, which are emerging as more reliable than others for the different reasons that I have stated regarding the transduction-based networks, but also entanglement networks. But that doesn't mean that in the future, the transduction-based networks and entanglement networks would not be good and reliable enough to have inserting them into modular architectures. We will see how it develops. But this is more relying on current state solutions, which are still not as mature as we need them to be in order to build reliable quantum communication networks. Okay, we can go to the next slide. Okay. Maybe before going to the circuit mapping and compilation techniques, maybe I can answer a few of your questions. I think I've went through many slides, so definitely you have maybe comments or questions that I can answer, or anything that you'd like to say. Okay, maybe I can take them from the chat because there is already 34 messages.
There are some questions on the chat. There were some quite concrete questions regarding
Okay,
specific
I'm
concepts,
trying
but
to open them.
let's look for some general questions.
Okay, gosh.
There are some questions.
Okay, L and A. L is the length, and A is the area at the intersection between the qubit and the communication channel. So these are two elements which we take into account in order to consider the area efficiency. If we have a large A mainly, that is the interface area, then that means the connectivity between the qubit and the communication channel would be too hard, and therefore the G factor would be low. So it's mainly two elements that we consider in order to position the qubit such as G is maximized.
Earlier, there was a question about CCR. Can we implement the CCR with IBM Qiskit? I'm not sure if it has been answered.
I think so, yes.
Yes.
I think so,
Okay.
because from IBM Qiskit, you can get the compiled code that would give you how many swap operations were added. And therefore, you consider these swap operations as your communication operations and everything else as your computation workload. And then you just do the ratio between these two.
Okay. Good.
Can you talk about IQM?
Yes.
Yeah, can you little bit about whatever you think about IQM? Yeah.
Okay, so interestingly, I met with IQM recently, and we had a specific discussion regarding their star topology. So their idea of star topology is not as simplistic as I have presented it, which is having one qubit at the center and every other qubit is directly attached to it. They will have multiple nodes of this star topology architecture, in the sense that even other qubits, which are considered peripheric qubits, will be the central node for another star topology. And that's how they are planning on expanding, on scaling the number of qubit per QPU. So at the very elementary level, yes, they are considering star topology, but for the scalability, all the other peripheric qubit can be considered as central qubits to star topology. And they said that it is a viable architecture for them. So they definitely did their benchmarking. And I think at this point, what we can do is just to take their word for it.
There's a question on the chat.
Mhm.
Or this is simulation, or you use any cloud-based photonic quantum processor.
Sorry, Paul, could you please
Yes, so this is the last question from Shafiqul. Is this a simulation, or you use any cloud-based photonic quantum processor? Maybe Shafiqul could unmute and clarify.
Okay, so this is not a simulation, this is a compilation. So what we use is mainly OpenQL from TU Delft. So practically, this is something like Qiskit, but it's not attached to any physical hardware, at least the ones that we used. And technically speaking, you can generate circuits for any size that you want. So that's how we could get to 1,000 qubits and even more. And then we just generate the architecture using OpenQL as well. So they support the generation of hardware architectures, and they also support the generation of circuits that you want to implement. But also, I wanted to hint that the modular compilation algorithm that is implemented in OpenQL is a very specific one. It is coming from a paper by Baker et al. From Chicago University, and it appeared in 2020. And it was the first algorithm that considered a modular architecture. So that's why we use it, because these works have been coming up since 2022. So that's why maybe they are relying on some old algorithms. But this algorithm, I would say, is mainly considering an all-to-all connectivity between processors, and it doesn't consider the architecture between the qubits in the same processor. That's on us. We can define that. We can rely on OpenQL compiler to deal with that. But for the intercore distribution of communication operations, we relied on the algorithm that is proposed by Baker et al. Maybe I can share the paper in the chat later on. But it's just to say that we considered very specific elements to do this analysis, and technically speaking, this can be expanded to other works.
Okay, so this is OpenQL platform, and but you're not sure about the qubit, whether these are polarization. Are you using photons polarization?
No, this is not really considering any type of hardware. I don't want to say it's hardware agnostic, because technically
Okay.
I did not use any hardware per se. So it's more of a compilation. So I stop at the code that will be the final result of the compilation. That's it. For the architecture, it's just a JSON file that would tell you what is the possible connectivity between qubits and how you can distribute your qubits over cores. That's it. But definitely speaking, experimental testing is very important. But up to this point, there is no modular architecture processor. Maybe when IBM will release theirs, then that would be helpful to do these tests. But up until this point, unfortunately, we cannot move past the compilation stage.
So it's
Okay.
suggesting that you propose compilation techniques regarding the architecture and the metrics are generic to any type of quantum computing hardware.
No, they are general. They can be applied with any type of hardware.
Yeah, that's good. Yeah, thanks.
Thank you.
All right, do we have more questions?
Mhm.
So, Sahar, I think we can continue, and maybe
Okay.
there will be more questions later.
Okay, perfect. Okay, so this is the last, I would say, couple of slides that I have. Thank you already for your patience and to get to this point. So this is for circuit mapping and compilation techniques for modular architectures. I will be mainly presenting the work from my colleague. Pau Scoffet. But of course, if you are interested in this area of research, then I definitely recommend that you take a look at his work, and you will find much more details in these works. Okay, so in order to optimize the communication overhead, we need to take into consideration what type of communication primitive we are using. So Pau has proposed the Hungarian qubit assignment algorithm proposal. This is already inspired from classical compilation techniques, which are used for modular processors, classical processors. And it is mainly aiming for minimizing the number of communication operations applied. Okay, so always we want to have an efficient compilation phase, because it will determine what type of operations will be applying at the end stage, which is mainly connected to the hardware architecture. So in this work, we are mainly assuming a communication primitive that is relying on entanglement generation and distribution. Okay, so that's why we consider an all-to-all connectivity between qubits, because this setup allows it. But also, this means that we will be taking into account the distribution of these operations across cores, and it will take into account the type of operations that is involved in the protocol itself. Here it's the teleportation protocol. So besides the EPR per generator, there is a step of post-processing, which you may be familiar with if you are familiar with the protocol of teleportation. So what is the challenge here? If we look at the circuit, this is the virtual circuit, okay? This is a circuit that has 4 qubits, and we mainly look at the application of 2 qubit gates. In this case, we have the C0. If we have a discrete timeline, or let's say execution time, then we may see that in some time slices, we have the application of operations among qubits which are directly connected, and that's easy. But in another time slice, we may find that we have to insert some changes to the circuit in order to bring the 2 interacting qubits into physical proximity. For example, we have this C0 gate, which is applied between Q0 and Q3. And therefore, it cannot be applied directly, simply because Q0 and Q3 are far away from each other, and therefore we need to bring them into proximate places, or let's say placement. And then for the third time slice, they are already close to each other, so we can implement them directly. Okay, so from this virtual circuit, we need to know how to move the qubits such that at each time we need to apply the C0, we are sure that the 2 qubits are placed in the same processor. So in the first time slice, we have Q0, Q1, easy, we can implement the C0 directly. In the second time slice, we have to move Q3 to core 1, and that means that we need to put the Q2 in core 2. Okay? Yes, maybe one detail is that we consider 2 qubits per core, and that means we have 2 cores. And in the last time slice, we have the application of C0 between Q0 and Q1, so we need to make sure that they are in the same processor, and also Q2 and Q3, so we need to make sure that they are in the same processor. And that's the logic behind compilation. Simply, every time we need to apply a C0 gate, we need to make sure that the 2 qubits are placed in the same processor. Now, in order to have these constraints added into the compiler, we usually define a cost function, and this cost function would take into account the condition that whether there are available qubits to transmit the states to in the core, and whether the 2 interacting qubits are placed initially in the same core or not. If not, they need to be moved, and of course the placement of these 2 qubits. So technically speaking, whether the two cores are adjacent to each other or not. If they are not, then you need to take into account the additional cores, the additional movements that you need to implement for bringing the two qubits into proximity. But of course, there is more detail into the paper, but this is more of a work in order to minimize the number of movements inserted. And eventually, this work has achieved, I would say, an increase in the execution time, but a decrease in the number of communications. And of course, I need to emphasize that your cost function, you need to define it according to your objectives. The objective of the HQA algorithm was to reduce the number of communications, and that resulted in increase in the execution time. But of course, if your objective is to work on both conditions, which is to reduce the execution time and the communication and the number of communications, then you need to update your cost function such that it takes into account these two constraints. Okay, can we go to the next slide, please? Okay, so HQA, so by the time this paper was released, there were two other alternatives. So we have the HQA, which was the proposal. We have the FGP ROEE, which is the one that I talked to you about, which is the Baker et al. Proposal, which I used for my work with OpenQL. And there is also another type of compiler that is relying on Kubo in order to find the best combination of movements of qubits in order to do the minimization, which is more of using quantum computers for quantum compilation, which is a very interesting work. And then we have more of a heuristic method for the distribution of gates. Of course, we are expecting that this would not be a scalable solution. And having more structured compilers would be, usually it would give better results. So we have the HQA as the blue line. Usually the metrics that we take into account for benchmarking between the different proposals are the number of non-local communications or number of additional operations for communication, the execution time of the circuits, the improvement ratio, and the speed up. The speed up is mainly regarding the execution time. So if we look just for the number of non-local communication operations added, HQA, I would say, is outperforming the other alternatives. Kubo may not be the best alternative at this point, technically speaking, because there is also a lot of work that needs to be done on the Kubo subroutine itself. But of course, it is still a very interesting area of research in how we can use quantum optimization for efficient quantum compilation. Okay, maybe also for the execution time, usually that would depend on the size of your circuit and the number of non-local communications added. But of course, we need to take into account the execution time, especially if we want to test these solutions on hardware. At this point, it's mainly at the compilation level. It may not be much of a concern. But of course, if we want to move forward into efficient compilation techniques for hardware, then we need to work on reducing the circuit depth and reducing the execution time. Okay, can we go to the next slide? Okay, there is also a very interesting line of research that has been proposed by my group as well, which is using deep reinforcement learning in order to optimize the cycle of qubit movements. So the hard mask algorithm is what my group colleagues have come up with, and they also compared it with other, I would say, alternatives that are also related on to deep reinforcement learning. And eventually they found a way in order to use deep reinforcement learning in order to optimize the compilation techniques. And of course, if you would like more details, I think referring to the papers would be best at this point. But I'm just trying to present to you the different proposals for the compilation techniques and what are the different directions which are considered in this line of research. Okay, Next slide, please. Okay. And there is another algorithm which is different from the HQA. It's called root forcing algorithm for circuit mapping. This also is very specific because it considers a 2D grid architecture between the cores, but also within one core. So this is the architecture that is being considered, and therefore the compilation algorithm is mainly built for this type of architecture, which may be prohibitive for the scalability, or let's say for the adaptability to other types of architectures. But we need to keep in mind that the 2D grid architecture is also a very viable type of architecture that is considered for scaling quantum computers, and therefore this is still a relevant assumption. And interestingly, the root forcing algorithm is built such that it can be used on modular architectures, but also on monolithic architectures. Why? Because since it considers that every two adjacent QPUs are linked by cavities, or let's say direct links, then that means that we can apply swap gates. And therefore, we can generalize swap gates such that it refers to intra-core and inter-core communications. So that's why it is a viable, I would say, algorithm to consider even for large-scale modular architectures. But interestingly, the cost function that is considered in this work is relying on what we call the position vector, I would say, of the qubits, that considers the original position of the qubit or the placement of the qubit, but also in which direction it needs to move in order to choose the optimal path. The optimal path can be chosen over how many swaps that you need to do, but also what is the fidelity of the links that you will be needing to cross. So this is also very interesting work because it takes into account the hardware constraints, that means the errors which are induced by the movement of qubits, but also it considers how many movements that you need to do in order to reach the target position. I think the root forcing also is very interesting algorithm to look at, and it has achieved, I would say, good results. Achieving a compilation average speed up that is almost 4 times the Sabre algorithm. Yeah, this one was benchmarked against this Sabre algorithm, which is the compiler of IBM Quantum. And it has reduced the depth of the mapped circuit by almost 5%, 5 times, sorry. However, at the expense of adding more swaps. So we reduce the circuit depth. So that means the time slices that we use to discrete the execution time. And yet we have added more swaps. This is mainly to say that there are different metrics that you need to take into account, and depending on your objectives, you may adapt your cost function as you like. Okay, maybe we can go to the results section of this part. Yeah. So yeah, there has been also a definition of a figure of merit that would enable us to have the best parameters, or let's say hyperparameters of our algorithm, and it has been tested on the compilation of different algorithms. And the metrics which have been considered are the execution time of the circuits, the depth of the circuit, and the number of additional swaps. And as you can see, also the structure of the circuit is very much an important element to take into account in this work. And we are trying also to find a way to build a standard compiler that will be efficient for all types of circuits eventually. But at this point, also we need to associate the gate distribution to the compilation so that in the future we may find a standard application. Okay, can we go to the next one? Yeah. As I said, the Sabre algorithm was the benchmark algorithm in this work. So everything that has been done in terms of comparison, it has been considering the Sabre algorithm. And yes, basically the root forcing algorithm was mainly successful in surpassing the root forcing in terms the Sabre algorithm in terms of time ratio, circuit depth, and swaps. It was mainly uh, almost the same number of swaps added, but at least there was a reduction in the depth and the execution time. So there is still, of course, improvement to do in this sense, the swap ratio. But I think we are still moving forward into optimizing and making this algorithm more efficient. Okay, and the next slide. Okay, so thank you so much. This has been, I think, more of a long presentation, but I'm very happy that most of you stayed until the end. Thank you so much for your patience. I hope this was very interesting to you, and maybe this was a new, maybe research line that is being discovered and presented in this session. But also, I wanted to say that there is also very active area of research considering quantum error correction for modular quantum computers. And of course, eventually, if we want a stable and scalable quantum computer, then we have to take into account the quantum error correction, even though my group is not really specialized in this area. Uh, and I don't think I will include it in my PhD, but definitely it's a very interesting area that I personally also would like to tackle. And yeah, I really hope that this has been very interesting to you. And I just wanted to also add the direction of quantum error correction as a way to integrate in this type of architecture, and it's a very important one.
Hmm. Great. Thank you very much, Sahar. Thanks for this great presentation. Can see that we still have a few questions on the chat.
Okay,
Um, so there was a question about the slide 28. What is the link?
28.
Yes, 28, yes. What is the link of the cited paper and how to define soft mask and hard mask?
Okay, to be honest, I don't have much of details of how they were defined, but I can share them. And if your specialty is in deep reinforcement learning, then maybe you'll have much easier time than me in understanding it. Um, okay, let me share the archive paper. Deep reinforcement learning. So again, in this paper, my part was mainly providing the compiled circuits, and definitely my colleagues worked on updating the compilation technique in order to include DRL. I hope it's easier for you to understand it, but yes, it was mainly to try to find a better way of achieving the minimization of the cost function according to the objectives that were set.
Mhm. Good. Yeah, there was also an earlier question from David about quantum errors. Have you considered quantum errors? I think you've partially answered this. Have you done any experiments beside theoretical analysis? I'm not sure if you would like to say more about it.
So for my work, since I'm mainly working with circuits of thousands of qubits and in that sense, since I don't have any experimental setup, then I personally did not work on that. But my colleague Pao, who is mainly specialized in the compilation techniques, he updated the root forcing to include the fidelity of the links. So that mainly characterizes the errors which are induced at the hardware level. And also, he has experimental tests on a test bed in Galicia. that's also trying to optimize his compilation algorithm according to the errors induced at the hardware level. So yes, there is definitely effort into orienting all the results towards a hardware, hardware aware, let's say, solution. And in my case, I am working with a group in Germany in order to optimize the qubit to cavity coupling strength so that we maximize the fidelity of the quantum state transmission. So part of my work will be, I would say, validated experimentally, but it's not the characterization part. It's mainly the qubit cavity coupling strength part.
Mhm. Okay, there was a question from Greg. Would you return to the correlation slide? Cannot find it in the archive publication. I'm not sure which page was it, and Greg
Yeah.
didn't get the page number as well, but maybe you remember.
Correlation, I am not sure. So maybe, yeah, we can go through the slides, and if the number of slides is clear, I think we can
Greg,
see.
please unmute and tell us if you see the slide that was interesting for you.
I thought it was in the teens. So 15, 16, 17, maybe.
Okay.
And it was just text. There weren't any images on it.
What's the next?
Keep going.
This one?
No, keep going. Right there, I think. Hold on. This one. Coupling
Okay.
strength. No, yeah, there it is. Coupling strength. I'm sorry. I said correlation. Thank you. Right there for a minute.
Okay. So is there a question regarding the coupling strength?
No, I just wanted to read it a bit more.
Oh, okay. Yeah, sure.
Okay. Nice. Good. Do we have more questions? I see
Yeah.
there was also a question from
Question
David.
there.
Yes, Caetano.
You mentioned about this quantum entanglement teleportation for communication between the quantum processes. I wonder if does have to be quantum entanglement teleportation, or could be any other means of communication because of the stability or fidelity of this entanglement teleportation, which may not be robust. And also you talk about the proximity of the processes, if they are close. So why do you need this quantum entanglement teleportation? Why not using optical communication between the quantum processes?
So at this point, most of the work is focused on optical communications for QPUs. But that doesn't mean that there hasn't been past proposals, especially the early ones. They were mainly relying on entanglement generation. I am not sure why there has been a shift. Apart from my opinion, which is it would be very difficult to insert an entire setup for entanglement generation and optimization and distribution for a modular setup. I mean, we need to think of modular architectures as QPUs, which are installed in cryogenic fridges, which are already very small in terms of size and in terms of how much they can hold in terms of electronics, right? So definitely optical communications and relying on quantum state transfer and entanglement generation through cavities is the most viable approach. For entanglement, I think it's mainly reserved for distributed quantum computers, which is different from modular. Distributed is mainly relying on long distance communication, which is mainly for quantum internet and interconnecting multiple farms of quantum computers. And I think in that sense, yes, they will be working on quantum entanglement generation to also take advantage of the security of quantum communications. But for modular, I think it will be mainly focused on optical communications.
Yeah, thank you. Thanks.
Thank you.
All right.
Okay. I think there has been also a question which universities are active in quantum
Yes,
research
yes.
besides UPC and UPV. So UPC and UPV are focused mostly on architecture and algorithms. There is ICFO, which is one of the institutions which is specialized in theoretical physics and quantum optics. It's also hosting a lot of research groups working in quantum computing in different aspects. There's also Barcelona Supercomputing Center, which hosts two types of quantum computers, one from IQM and one from Kilimanjaro. So that you can also access experimental tests with that. You have UPM, which is in Madrid, but their most important focus is on quantum communications. They have a lot of test beds and even prototype networks for quantum communications based on QKD, quantum key distribution. There is also Galicia. Galicia also has a supercomputing center, and they also host a quantum computer there. I think it's from IBM Quantum. And also they have the Basque country, which is at the north of Spain. They already host one of the research offices of IBM Quantum, and their systems are mainly IBM Quantum system. I think it's still System 1. Maybe they will get System 2 soon. But this is just to say that there is a lot of research groups and universities and institutions, especially working in quantum computing, and therefore I think Spain already has a good infrastructure for this type of research. Okay.
Mm-hmm.
Thank you so much, Greg and David.
There was
Okay.
just a question about is a number of quantum states related to the connectivity in any way? It's a question from Lido, Aaron.
Is the number of quantum states related to the connectivity in any way? You mean number of quantum states to be transmitted? Yeah, if you could maybe add a few details.
Yes, maybe
Or
you can unmute
exactly, yes.
and explain in detail.
Sure. Hey, thank you very much for your presentation. I'm new, so maybe the terminologies might be a little off too. I apologize. But yeah, just related, I'm just curious, we were talking about connectivity, and often a limitation in at least classical systems is bandwidth. So I was just curious, related to quantum states, if there might be any relation to, quantum states, bandwidth, and maybe any limitations on a connectivity, like maybe only certain number of quantum states per connection, or just wondering if there's any relationship between those phenomena. Thank you.
Thank you. So what I am aware of, there is definitely ongoing work on determining what is the bandwidth of quantum communication channels. That is very similar to how it is being quantified in classical communications. But I think at this point, experimentally speaking, it's still very low. And why is that? It's because the success probability of transmitting the state from the qubit to the photon is already too low to talk about, I would say, a deterministic state transmission. And also, the cavities are still quite lossy, and therefore you need to do the same operation of generating the state multiple times in order to increase the success probability. So I think at this point it is still very low. I do not have a number, to be honest, but I am assuming that definitely if we successfully improve the quality of cavities and the success probability of generating the states and transmitting them, especially with high fidelity from the qubit to the photons, then I think that will contribute to a better fidelity of the process, and therefore it will be more meaningful to talk about the bandwidth at that stage. But at this point, I think it's still too early to even quantify it properly, or even to talk about a bandwidth in quantum communications. I hope this answers.
Thank you. That was perfect. Thank you.
Thank
Also, a
you.
question from Jordan. Will you be moving to 3D architectures in the future?
So for 3D architectures, to be honest, I considered the 3D architectures at the beginning of my PhD. But then conceptually, it was a bit difficult to add that conceptually within a compilation framework. So at this point, I am mainly working on 2D architectures, which is at least how we are still scaling quantum computers, at least in the short term. And eventually, if we have more of an understanding of what a 3D architecture conceptually will look like, I think it will be much easier at that point to have that inserted into a compiler and eventually do the right tests. But yes, I definitely considered it at some point, but then it was a bit too difficult for me to work with since I really cannot visualize it or even conceptually understand it at this point.
Thank you. All right. I do not see more questions now. Would someone like to ask another question, maybe? Unmute.
I'm pretty new to all of this. Just wondering, like, how do you actually swap two qubits?
So the idea of swap is that you have two qubits and you just transmit the state of one to the next. So that's how we, let's say, swap the states. And I know how it is physically implemented in IBM quantum systems. So technically speaking, you just send a control signal that will have the frequency that is the difference between the two qubit frequencies. And with certain tuning of the phase control as well, you can successfully implement the swap. So this is mainly at the physical level, but also you may find in compilation papers, but also in experimental papers, the implementation of the swap gate as the sequence of 3 CNOTs. Yeah, so you have two qubits, you have a controlled NOT from the first to the second, and then from the second to the first, and then from the first to the second. And eventually that will swap the state between these two qubits. And this is becoming more of a standard, I would say. Yeah, let's say hardware aware execution of the swap operation. So it depends on how it is implemented in the hardware level. So what I am aware of is these two approaches, the physical one and more of the algorithmic one.
Sounds great. Thank you.
Thank you. For the slides, yeah, I think, yeah, I can definitely share. But there are just a few slides which are in preliminary results, so I will trust that you will keep them for you because this is still a work in progress and therefore it's not even published on archive and therefore it would be maybe a bit sensitive to share at this point. But yeah, I can definitely at least share the slides which are based on published papers.
All right, thank you.
Thank you so much.
Yeah, I do not see more slides. Anyone else would like to ask something? I think it's the last chance. Okay, I think we can finish for today. So Sahar, thank you once again.
Thank you so
First for
much,
the great
Paul. Thank you,
presentation
everyone.
and for answering all the questions patiently. So we had quite an interesting discussion at the end. Thanks for that. And we also thank everyone for staying with us until the end and also asking all these questions. We hope you enjoyed and hope that you will join us next week for the next meetup. Thank you.
Thank you. Good luck. Bye.
Bye-bye.